Okay. So when we increase a concentration, we're going to go through this first part fairly quickly because we've talked about it the last couple days, okay? When we increase a concentration, you can see that we go from having a smaller number of particles to having a larger number of particles. I'm hoping that it's really obvious that that will increase the frequency of collisions. Is that fairly obvious? Okay. Now, the one that's maybe not quite as obvious is that there is no change in the, and this is the key word here, in the percent of collisions which are successful, okay? So over here where we have a lower concentration, we might say maybe 20% of those collisions are successful. In other words, they have enough energy. When we increase the concentration, the speed of the molecules stays the same, okay? So the speed of the molecules stays the same. And if the speed is staying the same, then still it's only going to be 20% which have enough energy. Is good? Okay, so still 20% have enough energy. So that's what we're talking about when we're talking about the percent. Okay, still 20% and 20%. Now let's say over in this beaker that we have 100 collisions total. Yeah? And then over in the more concentrated beaker, we have 1,000 collisions total. If we have 20% of 100 which are successful, how many successful collisions do we have? That means, yeah, we have 20 successful collisions.
To the interruption. Attention all teachers who have grade 9 classes.
Thank God I don't have grade 9s.
Please report to the gym to help supervise Mountain Madness. Once again, anyone who teaches grade 9s in this last block, please report to the gym to help supervise Mountain Madness. Thank you.
It's just that the gym is so noisy and it smells bad. And it's like torture for me to be there. Like I'm old and I just don't need that. Okay. Like I get it that it's fun if you're participating, but if you're a teacher and you've had to go to Mountain Madness for like 24 years and you're like, okay, I've just had enough. I don't need it anymore. Anyway, so I'm really glad I don't have grade 9s this afternoon. Okay. Now, if instead of 100 collisions, we now have 1,000 collisions, but still only 20% of them have enough energy because the particles aren't moving any faster, then how many successful collisions will we have in total? We will have 200 successful collisions. So, yes, the total number of successful collisions has gone up, but the percentage of successful collisions has stayed the same, okay? Oops, total number of successful collisions increases but percent of collisions which are successful stays the same. Is good? Okay. Okay. So concentration is pretty straightforward. Pressure and volume. One thing to be aware of with pressure and volume is that it only works if you have at least one reactant that is a gas. Now, where are your reactants in the equation? Are they on the left or the right of the arrow? They're on the left. So reactants are over here and products are over here. It doesn't matter if you have a gas in the products because the product particles are not reacting. Only reactant particles react. Yes? So you cannot speed up a reaction by increasing the pressure if your only gas is a product. Does that make sense? Right? So if we had a solid plus B aqueous gives C gas, increasing the pressure will not speed up this reaction. Because C is not reacting. Okay, so you have to have at least one reactant, which is a gas. And this one works pretty much identically to concentration. Yeah, because you can see if we squish the gas, we go from a bigger area to a smaller area, we've essentially increased the concentration of the gas. So we get an increase in the number of collisions. Have we made the particles move any faster? Or are they moving at the same speed? They're moving at the same speed, okay? Same temperature, same speed. So although we have increased the frequency of collisions, are we changing the percentage of collisions which are successful? No. Okay? If 20% were successful on the left, 20% are going to be successful on the right because the average energy of the collisions is the same. Okay? Okay. right, here's another way to look at it. I think I just liked this picture because it had the little arrows on it that show the speed. Essentially, the longer the arrow, the greater the speed. Okay. And afterwards, have we done anything to the speed? No, the speed is the same. So it's like if I had a bunch of you walking around the room. Yes? All right, and you're walking around the room. You will occasionally collide with one another, but you're only walking. Will the collisions be sort of moderate or will they be very violent if you're just walking? The collisions will be just kind of moderate. Yes? Now, if I squish the room and all of a sudden where this room is halved in size, but you're still walking, are the collisions going to be any more violent than they were before? No, because you're still just walking, okay? There will be more frequent collisions, but they won't be any more energetic. Okay. So if you increase pressure by decreasing volume, the rate increases. There is another way to increase pressure. And that is by adding an inert gas. Are any of you familiar with the word inert? It's going to be from the same root. Because if something has a lot of inertia, it tends to not change its state, right? Like, or not state, but like if something has a lot of inertia, it won't move as much. Yes? Like if you hit it with something. Yeah, so inert in this case means non-reactive, okay? And the inert gases, as Sarah was saying, the inert gases, these will be, for example, the noble gases. Occasionally, there are other gases which won't react, but we're not going to expect you to know which ones will or won't react, other than the fact that you should know that the noble gases have a full shell and they will not react with anything. Sometimes nitrogen can be a good inert gas because it won't react with a lot of things, but you're not expected to know that. Okay? Now, what does it look like when we add an inert gas, and why does that change the pressure? So here we have our initial container, our before situation where there is no inert gas. And then we add in the little black particles, which are the inert gas, and they also move. Okay, so they're also, moving about and whatnot. Okay. So the total pressure increases because there are more particles bashing into the walls of the container. So our total pressure goes up. Will there be more collisions between reactant particles? VW is between. Have a little discussion about that with your neighbor. Will there be more collisions between reactant particles? I love this. What do you guys think? Yes or no? More collisions or not more collisions? There will be more collisions in total because you'll have collisions with the inert particles, but will there be more collisions between the blue particles themselves? No. Okay, so these would be the reactant particles are the blue ones. Okay, or I guess they're gray on your page. Okay. So are there more collisions between the blue particles? No. Sometimes, a blue particle might bounce off a black one and then go hit a blue one. That might happen sometimes. But sometimes a blue particle might bounce off there might be another blue one over here and it's moving towards it, and no, it hits a black one and it bops away from it. So the inert gas particles will prevent as many collisions as they will cause between blue particles. Okay? Or you could call them gray, because yours are gray. I really wish I could get you a color book, but yeah. I don't think you want to pay 10 times as much as you're paying. Now, someone was asking in the other class, and they'd be like, why on earth would you add an inert gas? And I think the only reason to do it is as a thought experiment, yes, to say, oh, yes, we can increase the pressure and yet not have the rate increase. Yes? I don't think there's any particularly good reason for doing it in real life. It's just to be thinking about the fact that you can make the total pressure more because you've got more particles, but you're not actually having more collisions between reactants. Okay? So no change to rate. Change to rate. Okay. Temperature. Here's our little slow particles over here. Okay, they're moving, not too fast. Off they go. Now we increase the temperature, we heat it up, got our little fire here, and all of a sudden the particles are moving much, much faster. So this is as though you guys were walking around the classroom. Yes, blindfolded, of course. You would collide with a certain frequency. Now, if I all of a sudden said to you, run, what would happen to the frequency of collisions? It would increase. You would run into each other more often. What would happen to the energy of those collisions? Would they be more violent or would they be the same level of? They would be more violent. Yes, they would be more energetic. Okay, so we are not only increasing the frequency of collisions, but we are also increasing the percentage of collisions which are successful. Changing temperature is the only one of these factors that changes both the frequency and the percent of collisions which are successful. Yes. Pardon me? There is. We don't call it violent, though. We just say how much energy it has. And that's going to be measured actually by temperature. Because temperature is literally a measure of the kinetic energy. That's what temperature measures. So if you're measuring the average kinetic energy, you are measuring the average violence of that fluid. Does that make sense? Yeah. That was a good question. Thank you. Okay, so they collide more frequently, and they collide with more energy. So a larger percent will have sufficient energy. Yay! So in this case, we might go from having 100 total collisions. Yes? And then we have 20%, which are effective, equals 20 successful collisions. So that's like before, right? Now over on the right-hand side, maybe we've increased that to 1,000 collisions, but we've also made them more energetic. So maybe now 50% have enough energy. And so that's going to give us not 200, but 500 successful collisions. So it's like doubly effective. Yay. Surface area. Over here, we have less exposed particles. And in order to collide, the particles must be exposed, right? And over here we have more exposed particles. Therefore, more collisions. No, fewer collisions. Fewer, meant to say fewer. Now, the only thing that messes people up here sometimes is that we can say, oh, if we chop it up into smaller pieces, what will happen to the rate? And sometimes people think, oh, there's a smaller piece, therefore the rate will be slower because I have less. But you're not just chopping off one piece, you're chopping the whole thing into pieces and keeping it all. You're not just taking one little piece. You're taking all of the smaller pieces. Does that make sense? So if we have chalk, we have a piece of chalk or something like that, we could dump it into some acid. Okay, we've got a nice piece of chalk. You guys don't know what chalk looks like anymore, do you? Or do you? Yeah, you do? Okay, we don't have blackboards anymore, right? Okay, anyway, chalk, drop it in, it'll react. But if you take the chalk and you crush it beforehand into a powder and you've got all these tiny, fine little pieces, that's going to react a lot faster. Is good? Yes. Okay. So once again, we have more collisions, but are the particles moving any faster? Or are they at the same speed? Everybody's at the same speed. Therefore, there is no change to the percent of collisions which are successful because the energy of the collisions is the same. And now we get to talk about the word heterogeneous reactions. Surface area only affects heterogeneous reactions. Now, what the heck do we mean by a heterogeneous reaction? Do you know what the prefix hetero means? Hetero means different. Okay, so if you are a heterosexual, then you are attracted to people of the different gender. If you are homosexual, you're attracted to people of the same gender. And in fact, are you guys familiar with, do you know what the human species is called? Homo sapiens. And that's because it means that all within the species are like us, the people who came up with the name of the species, Homo sapiens. They're like us. Sapiens thinking, they think like us. Yes?
But what would a sapien look like then?
That is a very good question, because they actually have that prefix, the genus Homo, they have like, I don't know, there's a whole bunch of them. I don't want to say one of them because it's like, you know, doesn't sound good in a classroom. But anyway, do I care? It's grade 12. There's a species called Homo erectus. Okay, that's the only one I can think of. I'm like, great, that's the only one I can think of. Yay. Anyway, they're related to Homo sapiens, right? So they are like Homo sapiens in that they walk erect, right? Bipedal, right? Anyway, means the same. Moving right along. Okay. It most often involves at least one solid reactant, but there are other conditions where you will have it. Basically, what it means is that you have to have two or more different phases. Now, there's a little problem with the word phase because often when people hear phase, they think the state. Yes, like solid, liquid, gas, but it's a little more nuanced than that. A phase, different phases cannot mix with one another. So phases are basically areas of matter that cannot mix thoroughly. So for example, if we had oil, which is a liquid, and water, which is a liquid, those are both the same state. Yes? Liquid, liquid. But will they mix? No. Therefore, there are two different phases. There is the oil phase and the water phase. So even though they're the same state, they are different phases because they will not mix. And when they will not mix, what do we have between those two phases? There's a boundary. Yes? The oil can't get through the boundary. And the boundary is just a surface. There is a surface between the water and the oil. Yes? So if I was to take this oil and this water, and instead of having it in a beaker like that, what if I put it in a container like this? Yes, now my water phase is here, and my oil phase is here. What have I done with the surface between them? I've increased it. I've increased the surface area. Okay? Not that I think there's many reactions that occur at the boundary between oil and water, but in organic chemistry, you will have different liquids that don't mix, and you'll have one substance which is soluble in one, a different substance that's soluble in the other, and they will only interact at that phase boundary. And so you'll get a reaction happening right at that boundary. Okay? Not so important for grade 12 because we don't deal with funky chemicals like that. We need fume hoods and things, and we only have one. So, all right. So, heterogeneous reactions have two or more phases. Okay, so you need to have reactants that are in different phases. Once again, it has to be the reactants. I don't care if the product is in a different phase because the product does not affect how fast the reactants react. Okay? This is a stupid sentence, but there we are. It's a meaningful sentence. Only reactants matter because only reactants react. Okay? Products do not react. I say that, and yet all of unit 2, 3, 4, and 5 are all about reactions that go forward and backwards. So sometimes you have reactions where products react, but we're not there yet. Okay, so for the purposes of this one, we have only one-way reactions. Okay, one-way reactions. All right. Now, if you are in a homogeneous reaction, all the reactants are in the same phase. But that could include, let's say, water, which is liquid, and HCl, which is aqueous. Yes, those mix thoroughly. This is the key idea here, is that if things are in the same phase, they are mixed thoroughly. So if they're in the same phase, they are mixed thoroughly. So even though the water, which is a liquid, and the HCl, which is aqueous, even though those are different states, they are still the same phase because they are mixed evenly with one another. Okay? Okay, so let's go through our examples here of the different states and how they relate to phases and whether things are homogeneous or heterogeneous. So we're going to start with a solid plus a solid. I have the solid blue book and the solid yellow book. Will these two things mix thoroughly? No, therefore that is heterogeneous. I have the yellow book area and the blue book area. Okay? If I have solid and a liquid, like let's say I have my water bottle here, that's a solid. Yes, the water inside it is a liquid. Are those going to mix thoroughly? No. Now, what if we had some salt and we put it into water and then we dissolved it? Would that be mixed thoroughly?
Yes.
Yes. Do we still have a solid and a liquid though if we have dissolved it? We would have a dissolved solid is now aqueous, which is homogeneous. I'm going to put it in quotes because now that it's dissolved, it's no longer a solid, it is now aqueous. So the moment it is mixed thoroughly, it's not a solid anymore. So if you have a liquid and a solid, it's heterogeneous. When it dissolves, it becomes homogeneous. So a solid and a liquid, there is a phase boundary. They will not mix. Solid and a gas. I have the book. I have the air. Homogeneous or heterogeneous? Heterogeneous. Two phases, book phase, air phase. Yes? Now, what about solid and aqueous? So I might take a chunk of solid zinc and drop it into my aqueous hydrochloric acid. Is the solid zinc homogeneous with the rest of it, or is it in a separate phase? Separate phase, okay? You've got a definite zinc area, okay? Liquid and gas, those are different phases. Again, in here, I've got the liquid phase, and then above it, I have the gas phase. Now, there are some gases that can dissolve in water, but once they are dissolved, are they still gases? No, they are aqueous. Okay, so aqueous takes care of dissolved solids. It also takes care of dissolved gases. Maybe I'll take the solid out of quotes because it makes me feel a little weird to have that there. Okay, don't like it. So the moment a gas dissolves, it's no longer a gas. The moment a solid dissolves, it's no longer a solid. They become aqueous. Aqueous and gas, same thing, okay? Now, liquid and liquid, I don't know if you have heard this term before. It is called immiscible, which means unmixable, okay? So if we have a liquid and a liquid that are immiscible, for example, what's a good example of two immiscible liquids? Oil and water. You have two phases. Yeah? So that's heterogeneous. You have the oil area and the water area, the oil phase and the water phase. And there is a surface between them. If I have two things that are aqueous, they're both dissolved in water. Are they mixed thoroughly? So if I was to take some sugar and dissolve it in the water, and I took some salt and dissolved it in the water, would the salt and the sugar be mixed thoroughly? Yeah, okay. If I have some gas and some gas, are those mixed thoroughly? Assuming I've given it some time to like diffuse? Yes. All of these presume that we've been able to, give things a stir or give them time to move around, okay? Now, there are liquids which are miscible, in other words, mixable. So that might be, for example, water and ethanol. Okay, that's just regular alcohol. If you put alcohol with water, the two of them, they just mix together. All right, so that would be one phase. So, for whom does it matter if we have a homogeneous or a heterogeneous? Only for surface area, okay? Now, what if I had this reaction? AgNO3 plus NaCl. Can you guys predict the products of that reaction? We get AgCl and NaNO3. One of them is a solid, one of them is not. Which one do you think is not solid? NaNO3, because it contains an alkali, which is soluble with everything, and nitrate, which is soluble with everything. So this is aqueous, and this is solid. And I'm going to ask you, can this reaction be affected by changing surface area? Can the rate of this reaction chat with your partner about that? Okay, we're going to vote thumbs up for yes, thumbs down for no. I'm glad that most of our thumbs are down because even though there's a solid over here, does it matter? No, because it is a product. This over here is just one phase. So the answer is no. Okay, excellent. God, we only have 15 minutes left? Okay. Do we want to just go fast and then be done as quick as we can? Okay, we're not going to take a break. We're going to just go as fast as we can and then be done. If we're finished early, we're finished early. Okay? All right. Catalyst. Catalyst is a substance added to the reaction. So it is a chemical species. Added to the reaction, and it lowers the amount of energy required for a collision to be successful. So it lowers that required energy. So if we had a high jump competition and we had a whole bunch of high jumpers, you can imagine that more jumpers have enough energy to get over this bar. Yes? And fewer jumpers have enough energy to get over this bar. So basically what a catalyst is doing is it is lowering the bar. Yeah? It's saying you don't need as much energy in order to collide successfully. You can just collide with less energy and I will help make that an effective collision. So the catalyst kind of gets involved. You don't need to know how it does it yet. We will look at that later, like how it actually makes that energy barrier lower. But for now, you just need to know that it does. It does make that activation energy lower. So if we had 100 participants at this high jump competition, you can imagine that maybe only 20% can make this jump. Yes? But maybe 50% can make this jump. Yeah? So what we're doing is we're increasing the percentage of collisions which have enough energy by lowering the energy barrier. Okay? More collisions will have sufficient energy to react. A larger fraction of collisions will have sufficient energy to react. Now, there's actually a word for this specific amount of energy, essentially the height of the bar, okay? And that word is activation energy. So how much energy do you need to react? How much energy do you need to collide with? You need to collide with the activation energy, amount of energy, okay? So that's our new word. Okay, activation energy is the minimum amount of energy needed for a collision to be successful. Soon we will look at potential energy diagrams. Over this diagram over here is a potential energy diagram. And basically what happens is that the catalyst says, under normal conditions, you need that much energy to react. Activation energy can be represented by EA, okay? But if you have a catalyst, the catalyst says, oh no, it's okay, I'll lower it for you. I'll lower it. So we now have a smaller activation energy. I want you to imagine that we're all going to go bowling, okay? We're all going to go bowling, and we need to bowl our bowling ball over the hill. Yes? Bowl bowling ball over the hill. Now, some of us are strong. Some of us have maybe, played softball or something where you have to throw with great speed, so you're practiced at it. And some of us, like me, maybe are like not the strongest we've been in our lives, right? Because I'm now over 50 and my elbows are weird and they won't let me lift heavy weights anymore. And, maybe I'm not really good at throwing things, right? Because just maybe I'm not, all right? So some of us are better at throwing with great speed and some of us are not as good. But we're all going to go bowling and we're going to bowl our ball and hopefully get it over the hill. Yes? Which of these two hills will have a larger percentage of the class successfully get the ball over the hill? Second one. Yes? It's exactly the same thing as is happening in the reactions. Okay? So that's what's going on there. The catalyst just makes it easier to achieve. All right. Lastly, nature of the reactants. This makes one reaction faster than a different reaction. You can't change a reaction by changing the nature of the reactants, because the nature of the reactants is just what they are. Yes? So you would have to be comparing reaction A with reaction B. You cannot make a reaction go faster by changing the nature of the reactants, because you cannot change the nature of the reactants. They are what they are. Okay? So what we're going to do is we're going to look at a video that compares the reactivity of alkali metals in water, and we're going to see what their rates are like. Okay, so we're going to, I just have to grab this thing. I need to go there. Okay. I said open. Open. There we go. Okay. Cool. Open. Thank you.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick, let's see if we can really get in there. So this side will reflect a lot of light, the other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those three and I'm going to add them to water, and we can look at the kind of reactivity of those three alkali metals with water.
So we're going to look and we're going to see how much time it takes for each of them to react, which is going to tell you how fast the rate is.
So So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel.
Now, one thing I want you to notice is how much more gas is being generated by the sodium. Like the little piece of sodium is moving around more. That's because it's generating more gas more quickly, okay?
And then the last one, I'm going to go ahead and put my 2 pieces of potassium in that I've cut in half. So this is less potassium.
Now, pay attention to how long it takes the potassium to actually be just gone.
Than the other two, in terms of amount, you'll find that the reactivity is a little bit greater.
Bam, gone. Okay, so the potassium is all gone, all right? And the lithium is still going, yes? And the sodium's still going. I will actually do a sodium in water for you at some point this year, maybe on a sad little Friday afternoon or something, you know, when it's rainy out or whatever, and we can have like a nice little end to our day. But the only thing that's different about these, they're all alkali metals, they're all reacting with water, but they have different numbers of electron shells, and that's the nature of the reactants. You don't need to know that it's the number of electron shells, whatever. You just need to know that there is something different about sodium than there is about potassium, and therefore they react either faster or slower. Which of these 3 beakers do you think has the highest activation energy? Which one requires the most energy to have an effective collision? Lithium. This is the slowest one, so it has the highest energy barrier. This one has the lowest energy barrier. So basically that's like, you know, you're basically bowling on a flat, basically. Okay? So that is where we're going to end it for today. Your homework is pages 37 to 40. We are going to finish off 1.2 tomorrow. So if you are going to Mountain Madness, make sure that you drop by for 5 minutes or stay for 5 minutes or whatever. I'm also going to give you this reaction kinetics terminology. It's all the vocab for the entire unit. So you don't need to use it all right now, but if you want to look something up, you can, right? Like collision theory is in here, for example, 3 and 4. There we go. 1, 2, 3, 4, 5. There we go. Usually I don't test on Wednesdays. I like to test on Tuesdays, but yeah. Yeah, for sure. There you go.
Are we having to answer some like definition during the Friday's test?
Possibly, yes.
Only-
Okay.
Only definition?
Pardon me?
Only definition.
definitions, but I might ask you which of the following could be used to speed up this reaction, or how does this speed up the reaction, or, you know, that kind of thing. Work through pages 37 to 40. That'll give you a good idea to
Alright,
start with,
thank
okay?
you.
Hi.
I was gonna be like back like after like grade 3, so
Okay,
just getting the signs here.
okay, there you go.
Thank you.
Yeah, for sure. Excellent.